So chapter 8 is about a couple more kinds of reactions, acid-base reactions and gas evolution reactions. We're going to spend the bulk of our time talking about acid-base reactions. So first of all, let's start out with the definition. What Svante Arrhenius says, that an acid is something that produces H+. All right, so let me ask you, do you know what H+ is? All right, so you know what H stands for? That's a hydrogen atom, right? And if that's a hydrogen atom has a nucleus and an electron racing around it, right? And it only has one proton in the nucleus because its atomic number is 1. And so an H+ is really just a free nucleus, because it only has one electron, right? So if we lose that electron and get an H+, then this is really just a proton. Okay? But it's a hydrogen ion. Right? So an acid is something that produces a hydrogen ion or a proton. Now, the way that you've seen this in chapter 3, section 5, and in my conversations, I've said, all right, suppose we have an acid, and the way that you're going to know something is an acid is if it has a leading hydrogen in the formula, okay, or if its name is acid, but if you see HA, what's going to happen is this is going to go off. A is going to get the bonding electrons. You see these electrons right here? They'll be here, and that will be A minus, really, and it'll leave an H+ in its wake, or it'll leave a proton in its wake. And so Arrhenius says that an acid is something that produces protons. So can you see that here? HA produces conjugate base and protons. All right. So an example of that was HCl, which we named hydrochloric acid. And this produces chloride ions plus hydrogen ions, right? Another example was acetic acid, C2H3O2. It's kind of a messy formula there, sorry about that. Acetic acid. Can you read my writing? Acetic acid produces C2H3O2, right? And what are we left with, right? That part is here. We're left with acetate plus NH+. Can you see how each of these produces an H+, okay? And I'm going to say in solution. It produces that in solution. Those words are going to come out. I wrote that kind of small maybe for you to see on the video, but it produces this in solution. Now, the last thing I want to say about this is that this is almost always done in water. Almost always in agua, water. Okay? If that's the case, then this proton is dissolved in water, right? And I will tell you that if water looks like this, then H2O, or when it's got H pluses in it, the H pluses typically just tack on to the water molecule, okay? All right, so water plus hydrogen ions gives you this, all right? Remember the name of this? We memorized this before in chapter 3. This is the hydronium ion. Okay, hydronium ion. All right. So I think this next slide is a picture of that. Suppose that we've got a bunch of water molecules, and you have an H+ that is produced by an acid. So you HA produces that, right? Also, the conjugate base plus A minus. Right, but this is the part we're concerned about right now. This is an Arrhenius acid. That's an Arrhenius acid. And if this is in water, then what's going to happen is it's going to piggyback on top of a water molecule. Can you see an H2O here? H-O-H. H-O-H. You've seen these before. H-O-H. Those are my H2Os, right? What's going to happen is it's going to piggyback on top of a water molecule and give H, 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 right? H3O plus. All right? So if you add up all the electrons that I've been talking about and all the protons and all the nuclei and all the charges, you're going to find that they add up perfectly. They add up evenly. And so that's what the pluses are about. Now there's a lot there, and if you're not used to looking at pluses and minuses, then it may take some practice. Okay, now what is a base then? Well, Arrhenius says, Savante, guy with the mustache, says an acid is something, I'm sorry, sorry, a base is something that produces OH minus. What's the name of this? Please say it out loud. Say it before I do. Pause the video, look it up. You'll be better off if you do. OH minus is hydroxide. You need to know that. Alright, so a base is something that produces hydroxide in solution. Oops, I just used that term again. That little qualifier, in solution. Or in water. I think all the solutions we're worried about right now are water solutions, okay? So this produces OH in water. So we might think about a base as something that does this. BOH gives B plus OH minus. Now, another thing you should do when you're watching me do this stuff is you should be adding up the charges. So to help yourself, to help this stuff settle in your head. So you should agree with me or disagree with me. So what's the overall charge here? BOH. It's neutral, right? What's the overall charge here? Aha, it's minus. Look at that minus there. So I need to add a plus to the base. This is really now a conjugate acid of that base, or rather of this base. Okay, so BOH produces B plus OH minus. This is the part we're concerned about if we're talking about an Arrhenius base. Arrhenius base is something that produces hydroxide in solution. Okay, so a specific example of that might be sodium hydroxide. That's the most common one, I think, that we're going to deal with. You've already dealt with that in lab. Sodium hydroxide produces something plus hydroxide, right? So it's Arrhenius base. Okay? It'd be helpful to think of Arrhenius as a guy with a big mustache. Okay? I'm so used to looking at his mustache that I've forgotten what his eyes look like. So let's just say, and there's his lip. I guess everybody deserves an ear or two. Okay, so Arrhenius says that a base is something that produces hydroxide. By the way, the reason I keep saying Arrhenius is because there's a couple definitions of bases. And this was a super valuable one, and I want you to hear that name, look at it, think of it. Arrhenius base is something that produces hydroxide in solution. So sodium hydroxide produces something plus hydroxide. What do you think this something is? Well, it's everything it's everything from over here that I haven't shown yet, right? So it's going to be sodium. Okay. Now, another example of that might be magnesium hydroxide. Now, magnesium is going to have 2, right? Because hydroxides have a -1 on it. And you know magnesium is in group what? Where's magnesium? It's in group 2. I'm trying to sound like Sal Khan from Khan Academy. I need a deeper voice, but so far I think I'm getting there. So magnesium hydroxide produces what in solution? Well, it produces hydroxide, or else we wouldn't be talking about it in this slide, right? Magnesium hydroxide produces hydroxide in solution, and what's left? Well, magnesium 2 plus, and there's 2 hydroxides on there, aren't there? Okay, so here's another example of a base, because it's an Arrhenius base, so then it produces hydroxide in solution. Now there's another example that your book gives, which I think is interesting, and it's ammonia. Ammonia is really one of the most important bases that we had to do with. Here? Yeah, one of the most important bases that we had to do with. Now watch this. If that's a base, how can that produce hydroxide in solution? What in the world are you talking about? Well, it can produce hydroxide in solution if we think about, well, wait a second, these guys are always in water. And if they're always in water, then it can produce hydroxide by taking away a proton from there, right? So what's left? You fill in the box. You can either look at your book or figure it out. You really should try to figure it out before you look at your book. Okay, so those are Arrhenius bases. Now I've got another slide here that's going to help us think about this. First of all, a list of some common acids and bases. Okay, these are super powerful. These need to be memorized. Okay, these 3 are easy, I think, because on the periodic table, right, here's fluorine, here's chlorine. I know this is too small to see. Iodine and astatine, okay? So look at these 3 right here, chlorine, bromine, and astatine, or rather chlorine, bromine, and iodine are right here, chlorine, bromine, and iodine, right? So hydrochloric acid, hydrobromic acid, and hydroiodic acid. Those 3 are there, and so those 3 should be easy to remember. These are easy to remember because you've seen them. I don't know, you see them. This is what we put in swimming pools, muriatic acid. I think that's muriatic acid. Nitric acid, I believe we put that in swimming pools along with some other things. And sulfuric acid is, I don't know, that's what shows up in the news the most. I remember a story from a couple years ago that was so ugly I don't want to repeat it here, but H2SO4, nasty, nasty stuff. This one's the hard one to remember, perchloric acid. So if I was memorizing this list, I guess I would start with the easy ones, but I would keep that one in the corner of my eye. Perchloric acid, suspect. Okay, so these 6 acids need to be memorized. Here's some weak acids which don't need to be memorized. Formic acid, you would, I don't know, I can't think you'd ever get that question unless you were told what it was. But acetic acid, you know what acetate is because you memorized it. C2H3O2 minus, right? And if we put an H plus on the front of that, right, then this is going to be HC2H3O2, right, which is acetic acid. And that's what it is right there, right? This is acetate. This is a hydrogen ion. Do you remember this from section 3.5? Acetic acid, right? We take the 8 and we make it ic acid. Okay. So those are some common acids. Oh, here's the point about ammonia, isn't it? We take some, here's some common acids, the 6 strong ones, 3 weak ones. I'll say more what we mean by strong and weak in just a minute. And here's some bases, which are really common. These are not all strong bases. Okay, actually, you know what? Strong and weak doesn't even show up here in this slide, does it? Okay, so let's move on. All right. Oh, yes. Okay, so if you have an acid and a base, oh, here's another point which does come up in this section. It turns out that this proton, right, this is aqueous, so we have an H plus and a Cl, an Na plus, and an OH minus. These guys go together to make water. Okay? And these guys go together to make nothing, right? Because they're still aqueous. maybe a decent time to review what we mean by molecular equations. So this is the molecular equation. The ionic equation would be H plus chloride, better write small, plus sodium plus hydroxide. Hope you can read this. Looks like I'm probably getting too small, aren't I? Gives water, right? This is no longer aqueous, and so it is not ionic. Plus sodium plus chloride. Right? Let me change my pen color. Whoops. Whoa. Let's go pen color blue. And let's get rid of the spectator ions. Sodium doesn't do anything. Look at that. Spectator. Oops, oops, oops. That's not a spectator. There's no hydroxide over here. But chloride is a spectator. Right? So here's the non-spectator. Here's the real actors. Right? See, everything's either circled or crossed off. So it looks like the net ionic equation is H plus hydroxide produces Vasa. Wow, that's it. Okay, so that's the net ionic equation. Now this kind of reaction here where you have an acid and a base that go together and make a neutral compound, you know what this is called? This is called neutralization. Neutralization. All right, so that's what this is. So we have an acid and a base coming together and they neutralize each other. If they're 1-to-1, they'll neutralize each other and make a neutral solution. If they're not 1-to-1, of course, it doesn't all even out. But we're supposing that they do go 1-to-1. And if you have enough of each, then they'll neutralize each other. Okay, so a picture then of a neutralization reaction is in your textbook. I don't remember what page this is on. But suppose you've got these two graduated cylinders which are pouring acid. This is HCl, right? And this one is here, that's base. Pouring these guys in together. And if you pour in equal amounts in, then what you're going to get is the hydroxides. This is going to mix with the hydronium to give two H2Os. Right? Can you see that? And you've got it here. HCl plus sodium hydroxide gives water and sodium chloride. All right. So this is just a repeat of what we saw on last slide. Okay, and I think the last picture we have is just a gas evolution reaction. So a gas evolution reaction, suppose we have, this can be complicated if we're going to study it deeply. Suppose we have here sodium bicarbonate. You recognize bicarbonate from your polyatomic ions table? Bicarbonate plus acid gives water and sodium chloride and a gas. Now, how would you know that? Well, you have to be told that. If you see a gas forming, know this is evolved gas, right? In other words, we're making gas, okay? And so if you're making gas, that's a gas evolution reaction. And the way that you know you have a gas evolution reaction is if one of the products is a gas. All right, I think that's all we've got to do there. We have a practice problem. Oh yeah, so type of compounds that undergo. This is just to give you a feel for it. You would again, you'd be expected to predict these reactions, but sulfides. If you have HCl plus potassium sulfide, you make Uh-oh. Make a gas. Okay? If you have carbonic acid, well, we're making carbonic acid here by HCl and sodium carbonate, you make a gas, right? Gas. Okay? Sulfites and bisulfites. So this is sulfonic acid. Wait. Sulfurous acid, sorry. Sulfurous acid makes SO2, sulfur dioxide, and that's a gas, right? I warned you when we're talking about gas evolution, we're not going to say much about it. Not now. So if we have ammonium chloride and potassium hydroxide, we are going to make, boom, a gas. Okay? So you have a gas evolution if you're making a gas, and you see 3 or 4 examples here. All right, I think I am going to skip this. Yeah, I'm going to skip this. I was going to say something about, I guess I will say this. This is a buffer. Carbonate, this is sodium carbonate. I will say something about this. Sodium carbonate breaks down then, watch this, to H2O plus CO2, gas, right? So this is interesting because you can take sodium carbonate and mix it with some pretty ugly acid, and it will give you something very innocuous, safe, and it'll make an acid, carbonic acid. But this carbonic acid is just going to break down to H2O and CO2, which will bubble off. Bubbles, be gone. Okay? So, very nice. All right, writing equations for acid-base reactions involving a strong acid. Write a molecular and net ionic equation for the reaction between, all right, HI and aqueous barium hydroxide. So this is a hydroiodic acid. Hydroiodic acid. Tro section 3.5. Consider going back and looking at that. And barium hydroxide. So write a molecular and net ionic equation. So the molecular equation is IO. This will be molecular. We'll change color for HI. For aqueous, right? You see that? It says aqueous HI plus aqueous barium hydroxide. This is going to produce, so this is going to, you've got hydroxides here and a strong acid, so it's going to produce lots of water, okay? So it looks like I've got 2 hydroxides, so it's going to take 2 of these to make 2 of these, right? Another way you can think of this is, there's my hydroxide from the base, and here's my acid, right? That makes it easier for me to think about what I need, okay? So it makes 2 waters. This is going to be liquid plus a barium, I guess iodide, right? Barium iodide, aqueous, because that's what's left. You see I've got a barium left, and I put barium here. Took 2 iodides to do this. Okay, so here's my molecular equation. Molecular equation. Now for my net ionic equation, I'm usually going to write out my full ionic equation first. Let me go red. For my full ionic equation is going to be H+. I'll put the states in a minute. Iodide. If barium hydroxide is aqueous, then barium is going to be like that, aqueous plus hydroxide. I realize this is not balanced yet, plus, or produces 2 waters, I got my state right there, plus barium, because it's aqueous, it's going to be by itself, right? Or it's going to be really with water, and iodide, and that's aqueous also. Let's go through and do the states. So these are both aqueous, aqueous, aqueous. This is aqueous, aqueous, and aqueous. Okay. Now, it looks like this barium is also aqueous. I guess I really ought to balance this first. That's probably bothering somebody, isn't it? Good. Should bother you. So it looks like there's 2 protons here, 2 iodides, 2 hydroxides, 1 barium, and 2 iodides. Can you see my 2 here? All right, now let's go through here and get rid of everything that doesn't change. Looks like my iodides don't change. Okay, my barium doesn't change, but my protons do. There's no protons here in the end. My hydroxides do, because there's no hydroxides in the end. There's no water in the end. I mean, there is water in the end, but no water up here. So that's what changes. All right, let me do this. Let me do my net ionic equation in red. Net ionic equation in red. I got some friends that are going to come in here. And I'm just going to tell them, just got friends that are going to come in. And I'm not going to say much. I'm just going to keep working here. I'm doing a video, so I'm not going to speak. Come on in. So for the net ionic equation is going to be 2H plus, I'll do the state in just a second, plus hydroxide, 2 hydroxide, right, state, gives 2 waters, and that's, I see that state right there. All right, come back and do the states. The state is aqueous and aqueous. All right, so this is my net ionic equation. All right, I think I've got one more problem to do here. Write equations for acid-base reactions involving a weak acid. All right, well, I haven't said much about weak acid. Let me say now that I'm going to try to be fast about this. A weak acid is something that yeah, I don't think we don't even need to really differentiate between a weak acid and a strong acid for this problem. Write the molecular equation, ionic and net ionic equation for this. I'm going to go fast. The molecular equation is H2. No, that's pretty bad start. Let me do it again. The molecular equation is HC2H3O2, which, by the way, looks a lot like HA, where that's my H, and here's my H, right? And the A just stands for that acetate, I guess. Agreed? I'll put the state in just a minute, plus potassium hydroxide. I'll put the state in just a minute. It says aqueous and aqueous. That should be easy. Produces, you know what? I'm going to go straight to the chase. The hydroxide goes off with the H. So it's going to be H2O, liquid, plus, and this is going to be potassium acetate, 2H3O2, aqueous. I know I'm going kind of fast here. All right, so this is acetic acid. Here's potassium hydroxide, and they're aqueous because the question says it is. All right. So the full ionic equation is going to be H plus aqueous plus acetate aqueous plus potassium aqueous plus hydroxide aqueous produces water, liquid, plus potassium aqueous plus acetate aqueous. Okay? So let's go now through. This is the ionic equation. I've got it here. Let's go through and get rid of the things that don't change. That doesn't change. That doesn't change. That's it, right? Everything else does. So it looks like our net ionic equation is H plus aqueous plus hydroxide. Aqueous produces water, liquid. Okay? So this is the net ionic equation. This is the ionic equation, and this is the molecular equation. All right, hope that's helpful. That's all for this section. Ooh, I was wrong. Okay. Okay, so write a molecular equation for the gas evolution reaction that occurs when aqueous nitric acid, let me go back to red here. Aqueous nitric acid and aqueous sodium carbonate are mixed, okay? So you've practiced with the name of nitric acid before. You might need to look that up. HNO3 is nitric acid, and that's aqueous, plus sodium carbonate. Sodium carbonate. And carbonate has got a -2 on it, so that must be +2. And that's aqueous, right? This you did in Chapter 3, Section 5. This you did in Chapter 3, Section 4. Okay? And these are both aqueous, and I can put the states in now. A little bit too small maybe to read. Nitric acid plus sodium carbonate produce what? All right, well, in order to solve this, I'm going to write out the ionic equation. Here's a good chance to see how valuable the ionic equation is. It's H plus, because it's aqueous, right? And it's nitrate. Okay, aqueous, oops, nitrate is a minus, plus sodium, aqueous, plus carbonate, and this is 2 minus, right? Aqueous produces what? Well, we know they switch partners. Remember we did that in the previous section. So the H pluses are going to go with the carbonates, and the nitrates and the nitrates are going to go with the sodiums. So it looks like there's going to have to take 2 H pluses, right? So let's make that a 2. And if that's 2, this is also going to have to be 2 because they came in 1 to 1, right? And that'll also have to be 2. Okay? 2 H pluses is going to give us, all right? Well, it's going to give us carbonic acid, right? H plus. And let me go back up here and put this in red, and we'll decide if that's going to be. This is going to give us carbonic acid, H2CO3. And that's going to be aqueous because we look up the solubility of that, right, in table 4.1, and we see that that's aqueous. It's carbonic acid. Plus sodium nitrate, aqueous, right? Just to keep my pen colors consistent. That's going to take, it's going to give us 2 of those. Agreed? See, 2 sodiums, 2 nitrates, right? Sodium nitrate. Okay. Well, these are all aqueous. So what that's going to do is it's going to give us, yeah, look at that. Okay, now here's we saw this. Here's the trick now. We saw this on page 157. We read on page 157 that carbonic acid, that breaks down to H2O plus CO2. I think I said this in a previous slide also. So H2O plus carbon dioxide comes from carbonic acid. So what's that going to give us here? That is going to give us color red. That is going to give us, or wait, I need black. Sorry. Black. That's going to give us H2O liquid plus carbon dioxide gas, and there's my gas, plus, and that's definitely going to be aqueous still, right? Sodium, that's not going anywhere. It's going to be sodium plus aqueous plus nitrate, aqueous. Okay. All right. So this is my ionic, my complete ionic equation, and I had to take a break when I first did this. Right. I first had to write these out and think, oh, I switch partners. Then I recognized, hey, that's carbonic acid, and I read on. Did I already say page 159? Page 159. That carbonic acid breaks down into water and carbon dioxide. By the way, this happens in your blood, and that's why if you have, if you don't breathe enough, you get too much CO2 in your blood, right? Which backs up a pipe into carbonic acid, and you are said to be acidotic, right? Your blood will become acidic if you have too much carbon dioxide. Because there's plenty of water, right? So the carbon dioxide that you're not breathing out, like you're supposed to be, if you're not breathing well enough, then your carbonic acid will back up and make carbonic acid in your blood. Okay, I didn't fill in the aqueouses here. I'm going to do that real quickly in case that's bothering anybody. Aqueous, 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 aqueous. Okay. Now I'm going to go through and do the net ionic equation, which I don't think I was asked to do here, but I'm going to do it anyway. Red. What doesn't change? Looks like the sodium doesn't change here, right? Sodium doesn't change. And the nitrate doesn't change. Okay, there we go. Nitrate doesn't change. So it looks like what's happening here is we're getting 2H plus aqueous plus carbonate aqueous produces water plus CO2. Very convenient. Very convenient. Look what carbonate can do. Carbonate, this is acid, right? So carbonate can take acid in your blood, which is the opposite of this, right? Can take acid in your blood. Carbonate can mix with it and turn it into water if you can breathe this stuff out. That's if you can breathe. Must, don't forget to exhale. Must exhale. Don't forget to exhale. Okay, and I think that's it for this section.